Thank you, Ferit. Good afternoon, everybody. I also want to give you an overview about the work we have done with the last 4 years with different radiolanthanides. And let me start with the big picture. In this room, I think we all aim to increase the number of radiolanthanides, which is in general radionuclides, in the last step of this radiopharmaceutical development pipeline. And if you look at this image for radiolanthanides, we already have 2 radiolanthanides which reached the final step. First one is lutetium-177, and the next one is terbium-161, which has received also high interest during the PRISMAP project from several users. And while I was preparing this presentation, I also wanted to update myself regarding the clinical trials currently ongoing with different terbium-161 containing radiopharmaceuticals. And here I would like to also show you this overview. The first one was registered by Australia. It is about the prostate cancer treatment with terbium-161 PSMA NIT. And the next 2 projects were registered by Basel University Hospital from Switzerland. It's a collaborative work between PSI, ETH, and University Hospital Basel. And the next one is from Israel. It is again related to terbium-161 PSMA INT. And actually, this last one I was not aware. And in 2025, another study was registered with terbium-161 PSMA compounds in China. This is about terbium, but our work was not only about terbium-161. We investigated several different radiolanthanides in this work package. That's why actually we call them radiolanthanides toolbox. Because if you look at nuclear chart, there are several radiolanthanides with proper decay emissions for nuclear medicine applications. And they have similar chemical behaviors, lanthanides in general. So thanks to this, they have analog coordination chemistry. If you want to prepare radiopharmaceutical containing radiolanthanides, it's a great advantage. But if you want to separate them, it's another story. And thanks to these similar chemical properties, actually, it allows us to perform systematic preclinical studies. And thanks to this, also, we can learn a lot of things about targeted radionuclide therapy, and we can answer basic questions. Last but not least, as I mentioned at the beginning, we already have clinically approved lutetium-177. Terbium-161 is on the way. And all the knowledge gained with these 2 radiolanthanides will certainly help us to increase the number of radiolanthanides in the final step. And here I would like to show you how our toolbox looked at the beginning of PRISMAP project. As you can see, we can fill all the boxes with different radiolanthanides. And during the project, we also made 2 additions, Hormium-166 and Hormium-161. And here I would like to show you actually what we proposed. We proposed to prepare 2 deliverables. First one was about the cross-section measurement. Second one, development of chemical separation techniques for different radiolanthanides. And third one was the preclinical studies. And concerning the cross-section measurements, we proposed to determine cross-sections for terbium radioisotopes. But on the way, also, we finalized the cross-section measurements for Hormium-161 and Thulium-167. And the first work I would like to report you that was performed by Aronax. They investigated the potential of deuterons for the production of terbium-155 by using enriched gadolinium-155 targets. And one of the drawbacks of this production route was the final radionuclidic purity of the sample, because by increasing the cooling time, we can decrease the radionuclidic purities of the short-lived terbium isotopes. But in case of terbium-156, which has a similar half-life like terbium-155, it was not possible. However, all the work has been done and published. And they also, same group, they also investigated the terbium-161 production using deuterons. First study was performed using natural gadolinium oxide, and second one was performed with enriched gadolinium-160. And both works were also published. And at PSI, we also performed cross-section measurements, as I mentioned, for Hormium-161 and Thulium-167. Actually, we divide our work always to 2 parts. First part, we performed cross-section measurements in collaboration with Bern University by using their medical cyclotron. So we can perform cross-section measurements up to 18 MeV. And in the second part, we also, after we finalize the cross-section measurements to validate our cross-section data and also to investigate different production rules, we perform production yield measurements by using injector 2 cyclotron of PSI. And here's the result for Holmium-161. We used natural dysprosium and enriched dysprosium oxide targets. Here you can see the results for PN and P2N reactions. And here you can see more comprehensive picture for the production yield measurements. Besides this dysprosium PN and P2N reaction, we also wanted to use our medium energy protons for the production of Holmium-161. So we investigated Holmium-165 PN reaction. So in this case, we can produce Holmium-161 via indirect production mode. And actually, when we compare all this production route, it was the most interesting one because we could reach pretty high radioactivity purities. And based on our actual measurements, we could, after 6 hours, it was possible to determine 15 gigabecquerel of Erbium-161. So which also motivates us to develop also chemical separation method for these radionuclides because it is relatively short-lived. Its half-life is 2 hours. If you consider also the chemical separation process, we would lose quite a lot of activity during this process. But since activity is quite high, at the end after chemical separation, the activity of the final product should be still enough for preclinical studies. And the next project for us was Thulium-167. Again, by using enriched Erbium-167 and 68 targets, we investigated the production of Thulium-167 via PN and P2N reactions. And this was the burnt part. And for the PSI part, again, we validate our cross-section measurements. And then we compare all these production rules. Erbium-168 P2N reaction was one of the promising one, but we cannot avoid the radioactive purity of Thulium-168 in this production part. And again, we investigated the medium energy protons, and we investigated Terbium-171 P5N reaction. It is again indirect production route for Thulium-167 production. As you can see, we could increase the radioactive purity by using this indirect production route. And if we look at our first deliverable, all cross-section measurements were finalized, and except the Holmium-161, all of them were published, and we are hoping to be published soon. We are going to submit very soon, I can say. And the second step was the development of chemical separation methods for radiolanthanides. And here I would like to also show you methods were developed for different radiolanthanides. Oh, sorry. Yeah. First one is lanthanum-135. It was developed by DTU group. They actually finalized all the steps from targetary irradiation and chemical separation steps, and they also published their work. They use two-step chemical separation method, DGA and TK200 resins, to at the end to elute lanthanum-135 solution in 0.01 molar hydrochloric acid. And as a result, actually, they received requests from SK-CEN to receive lanthanum-135, and they sent 5-page to SK to perform some preclinical studies with this radiolanthanide, which I am going to report also in the third part of my presentation. On the other hand, at PSI, we also wanted to investigate terbium-155 production with protons. We use enriched gadolinium-156 via P2N reaction, and we developed 3-step chemical separation method, DGA, second column, and LM3 column. And all these columns were used for the separation of gadolinium and terbium to secure the final quality of terbium-165, sorry. And as a follow-up, because similar to what I mentioned at the beginning when I talked about Aronnax cross-section measurements, then we use protons. Again, we cannot avoid production of terbium-156. Therefore, in the frame of PRISMAP Plus, we aim to investigate indirect production of terbium-155 via terbium-155 P5N reaction. Another very interesting radiolanthanides is Erbium-165, and this work again was done by DTU colleagues. They used LN2 resins like a repetitive way, and also as a final step, TK221 resin to elute Arium-165. But we also reported the deliverable. There's still room to improve for this production route. Actually, DTU colleagues are working to increase the production yields and to increase the separation efficiency. On the other hand, what Mikael Jensen actually always highlight, and he's totally right, and the quantification of Arium-165, which is very important, because once we bring this radionuclide to the next step for the preclinical investigation, we need to determine its activity precisely. So this is one of the things also we want to work in the frame of PRISMAP Plus. So we already actually tried to coordinate everything. So since also it has short half-life, transport will be a kind of big issue. That's why DTU agreed to host IST, ID, and KU11 colleagues in their facility to perform preclinical studies for PRISMAP Plus project. In addition, for PRISMAP Plus, we also aim to investigate indirect production route for Arium-165 via Thulium-165 decay. And if you look at the second deliverable, all the work has been done, what we promised. As you can see for Arium-166, I put a kind of green cross. The reason is, first reason actually, we didn't propose it at the beginning of the project. The second reason, we have already started to work on it. Actually, last month we received 2 samples from ULI, and we also checked our chemical separation method, and the results were quite promising. We could level 100 megabecquerel per nanomole with dodate, but we still want to investigate the generator concept, which will be also topic for PRISMAP Plus. If you look at the last step, our last deliverable, which was about the preclinical studies, I don't know if you can read. Yes, I think here is much bigger. We promised to do a lot, but we have also done a lot of things. I am only going to show you the work which we could end, which we could finalize with the publication. And I have already presented several times the work of Antonio and Frederick. This was always one of the highlights of work 12. They wanted to investigate the different Terbium-161 complexes targeting the mitochondria of prostate cancer cells. Here you can see they synthesize. You can see that they synthesize 2 complexes. One of them is DBP delta PSMA 617, and the other one is PSMA Terbium-161 delta G3 PSMA 617. And they compare their potential with standard Terbium-161 PSMA 617. Actually, before this study, I should mention that they performed all this work with Indium-111, which they also finalized and published. As a next step, they started to perform systematic study with Terbium-161 by using these 2 different complexes. And here you can see on this slide the control uptake study and both new complexes, what they synthesized. We performed the standard PSMA 617 complex. On the other side, you can see the chronological assays and survival fraction. By increasing the activity, again, these 2 compounds showed much less survival fraction compared to the PSMA 617. And they also investigated DNA image. You can see the microscope image. I think it's also clear for everybody that radiation damage caused, DNA damage caused by visual electrons, they investigated. And again, TBP G3 PSMA complex, based on this microscope image, they found that actually each chart was much better than the other complexes. And at KU level, they also performed animal spec studies, and in this case, they reported that the complexity didn't have a big effect on the quality of the spec imaging. And so far, I talked about the cyclotron-produced radionuclides, reactor-produced radionuclide, Terbium-161. And here I would like to also mention about, again, reactor-produced radionuclides, but not via indirect production route, via direct production route. When we want to produce medical radionuclides via gamma reaction, again, we use enriched material, but at the end of the production, we have the mixture of, in this case, for instance, samarium-152 and samarium-153, including other impurities. But what I would like to highlight here, after irradiation, we don't have samarium-153 with high specific activities, which means separation doesn't really help. we need to add additional step in our development line, which is offline mass separation. This work was finalized before the start of the PRISMAP project, just before actually the start of PRISMAP project. A rich samarium of 2 samples were irradiated at BR2 reactor in Belgium, and then several samples were sent to Sir Melis's facility for offline mass separation. And after SK colleagues, they received the sample back to perform chemical separation. And here you can see actually what I mean. These are the specific activities for the reactor to produce samarium of 53, and the one reported below is after mass separation. And what has been done in the PRISMAP actually, at the beginning of PRISMAP project, SK colleagues, they finalized their preclinical studies with samarium of 53 dolatane, which is a promising beta-emitting radionuclide. And they performed again very comprehensive study, in vitro evaluation of this compound, and also in vivo evaluation. They showed the high tumor uptake for with this compound. And also they performed spectrum imaging. You can see the tumor on the shoulder of the mice. I remember correctly, the first image was taken after 4 hours, and the second one after 24 hours. And they concluded in their article that samarium of 53 has a strong potential for targeted radionuclide therapy. One of the recent studies, actually it was submitted recently to European Journal of Nuclear Medicine and Molecular Imaging. It was again done by SKC and colleagues together with the support of the ETU colleagues, because they received the lanthanum 135 from them. If you look at their article, actually, they also highlighted the importance again to radionuclide quantification, precise activity measurement for lanthanum 135. In this study, they performed their studies with the dotatate agonist and the dotatate antagonist, and with vectors, and they performed radioactivity up to 50 megabecquerel per nanomole. And I also took only one image from their publications actually, but they showed here, due to the limited dose to the nucleus, they couldn't have a pronounced biological response. And in their article, they concluded that lanthanum 135 offers limited therapeutic potential for this study. About the preclinical studies, many things have been done, but we also learned a lesson, because as you can see here, this is an important point to highlight, we promised to do preclinical studies with many more radiolanthanides, but I must say that it was not really realistic, because radionuclide production takes time, and to include some radionuclides which were in development stage, to put them in brief to propose to perform preclinical with radiolanthanides was not really realistic. So the only last point we couldn't finalize in this whole package. If you look at the publications, I only listed the ones where PRISMAP was acknowledged. So in total, we have 10 publications. One of them is a review paper. And as I mentioned during my presentation, there will be 2 additional ones which we hope they will be published soon. Another point which I already highlighted in my previous presentations, if you look at the number of the user projects and the user projects which are related to radiolanthanides, almost 50% of them are related to radiolanthanides. And so far, only one of them were published. And actually, we were discussing with Kirsten today, and she mentioned to me that each user at the end of the project, they are asked to also prepare a report. I think this would be very useful to receive this, like all the TNA. It would be very useful if it is sent to all the TNA facilities, because also we are very curious about their work and how they use radionuclides and their studies in general. So I think Charlotte is following the presentation. So I think it will be very important and beneficial for us to receive this feedback. But I think also there will be more publications about user projects. If you look at the events, we organized 2 events. First one was PRISMAP Radiolanthanides Summer School, and second one PRISMAP Radiolanthanides Workshop. And the summer school was organized by DTU colleagues in collaboration with PSI and ILL. I think it was a great success. We received a lot of applicants. It was difficult to decide who to choose. Students were chosen based on their CV and motivation. And we hope actually to reorganize this summer school in the frame of Innovate Rad project. Concerning the workshop, which was organized at PSI. I don't know if you noticed, but we even have a logo for this workshop, which I always use when I talk about radiolanthanides. And this also received a lot of interest. And in this workshop, we really try to bring all the experts from the targetry to the clinical trials. We even organized a panel at the end to discuss the clinical trials and from different experts, because it is really multidisciplinary research, and we all need to discuss to bring all this interesting radionuclides to the next steps. I mentioned about several different projects, but there are still a lot of things to be done, which we aim to perform. Some of the work was in the frame of PRISMAP Plus project. And this is also a good opportunity for me to announce at PSI currently we look for 2 PhDs who will work on the production of medically relevant radiolanthanides, and one of them also will work on the chemical separation of radiolanthanides. It will be more fundamental research. If you know anybody who may be interested, it will be great. Please let us know. And I started my presentation with the big picture, radiopharmaceutical development pipeline for radiolanthanides. But I think there is another way to see this pipeline, which we call it the PRISMAP pipeline. For PRISMAP project, we have only one dedicated GRA for radionuclide production, it was radiolanthanides. But for PRISMAP Plus, we have 3 GRAs for medical radionuclide production, generators, novel metal radionuclides, and piezoelectron emitters, which I am particularly very happy about this. And in this case, my last word will be, we have done a lot, but we still have many things to do, and we can do it only together. So I would like to thank all the partners who were involved in PRISMAP during PRISMAP to accomplish the event. And I would like to thank Renata for the great organization. Thank you.